So the method to moments estimator provides a pretty intellectually appealing way of estimating the parameters of a probability distribution. Probability distributions have averages, samples have averages, so let's just pick the value of the parameter so that those two things match up. The average of the PDF matches with the average of the sample. But it turns out that there's a better way to go about estimating the parameters, and this is called maximum likelihood estimation. We'll get into the theoretical reasons as to why maximum likelihood estimation is really the way to go. But first, I do want to go through the mechanics of running through maximum likelihood estimation. Mathematically, it's going to involve quite a lot of work. Computationally, it's going to be very easy to do because fitdist is going to be able to estimate those parameters for us really quickly. But because this is the way that statisticians tend to estimate parameters of probability models, or even really sophisticated complex statistical models, we want to be familiar with the ins and outs of how the maximum likelihood procedure works. Let's learn about the maximum likelihood estimation procedure in the context of the following example. So let's imagine that we're trying to estimate the probability that a shopper is going to make a purchase at a store in any particular week. So we have 20 data points here. The shopper did not make a purchase week 1, but the shopper did make a purchase on weeks 2 and 3, etc. So if we think about it, what probability model describes the data that we're collecting? Well, in this case, we're essentially only recording yes or no if the shopper did or did not make a purchase. So this sounds like a Bernoulli random variable. Bernoulli random variable only has two outcomes, success or failure, ones or zeros depending on the notation, and that's our context here. So x1 in this case, our first value that we've collected is a 0. They didn't shop. x2, the second observation we've collected, is a 1. The shopper did make a purchase. x3 is equal to 1, x4 is equal to 0, etc. So what we have here is a sequence of outcomes of Bernoulli trials, ones and zeros, and we would like to estimate the p parameter associated with this Bernoulli distribution. What is that probability of success? What is the probability that the shopper makes a purchase on a particular week? So let's assume that all 20 of these data points are independent of each other. So what the shopper did in the past doesn't influence the probability that they make a purchase in the following week or weeks. Let's treat this as an IID sample. They're all coming from this Bernoulli distribution with parameter p. They're all independent of one another. How do we estimate p from the data? Well, let's do the sensible thing and say, okay, if this probability model is correct, what is the probability of observing this sequence of data? A 0 followed by a 1, followed by a 1, followed by a 0, etc., etc. Well, under the Bernoulli distribution, the probability of observing a 1 is just p. The probability of observing a 0 is 1 minus p. So we can write out the sequence of the 20 observations as follows. 1 minus p times p times p times 1 minus p times etc., etc. Since we're assuming that each observation is independent, the probability of that combination of outcomes along that sequence of size 20 is just the product of the individual probabilities. And so the equation for figuring out the probability of observing our data is particularly easy, just the product of observing what we did on week 1 times what we observed on week 2, etc., etc. So in the end, after we write that equation, we find that we would have p appearing in that product 7 times, 1 minus p in that product 13 different times, representing the 7 times the shopper did make a purchase and the 13 times the shopper did not make a purchase. So our equation simplifies to p raised to the 7th power times 1 minus p to the 13th power. So if a Bernoulli distribution is generating the data, the probability of observing our data with that probability model is as follows. Now, we're going to say the probability of observing our data is the likelihood of our data given that probability model. So what we've derived is the likelihood function of observing our data with our Bernoulli probability model. Now, the maximum likelihood procedure says, well, let's pick the value of p that maximizes this likelihood. Or in other words, let's go ahead and pick the value of p so that the resulting probability model, the resulting Bernoulli distribution, has the highest chance of reproducing the data that we've collected. All right, so we need to maximize that particular function of p. We can do that in a few ways. We can go and just make a graph. Look at this graph of what that function looks like, and we can visually inspect to see where the peak occurs. Looks like it occurs right at about 7/20. But normally what we want to do is find the exact answer either with Wolfram-Alpha or maybe running optimize in R, which is good for finding the peaks of curves. So one thing that we can note though about our plot about the likelihoods of the data versus the p parameter of that Bernoulli distribution is that we can't actually outright eliminate any particular value of p from the data that we've collected. If p was equal to 0.001, the probability of observing that sequence of no purchases versus purchases is very small, 9.87 times 10 to the minus 22, but it's still possible. So it's possible to observe our data if p was very, 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 very tiny. It's also possible if p was equal to 0.99. If we were to go and calculate the probability of observing the sequence of purchases, non-purchases that we observed, it would work out to be 9.3 times 10 to the minus 27, but technically that's still possible. So we can't outright eliminate any value of p from consideration based on the data that we've collected, but certain choices definitely make more sense than others. I think the choice that makes the most sense is where that probability reaches a peak, the maximum of that likelihood function, and that's going to be the philosophy of maximum likelihood estimation. We can never really eliminate any values of those parameters of the probability distributions once we've collected the data, but some values make a lot more sense than others. We're going to choose the value so that the resulting probability model has the best chance of reproducing the data that we've collected. In other words, maximizes the likelihood. So how can we come up with a more exact value than just eyeballing it? Well, we can run the optimize function in R, give it the function that we're trying to maximize, give it the interval over which we know that peak occurs, and set maximum equal to true. We get a value of 0.349999, suspiciously close to 0.35. So we can maybe ask Wolfram-Alpha to help us out, come up with a more exact mathematical answer. We can ask Wolfram-Alpha to maximize the same function between the range of p equal to 0 to 1, and it lets us know that actually that maximum occurs at a value of p of 7/20, which works out to be that 0.35. And so when we do maximum likelihood estimation, this is what we're doing. We're taking the very appealing stance that the value for the parameter that we should take that's defining our probability distribution should be the value that gives us the best chance of producing the data that we've collected. It's right in front of our face. Let's come up with the probability model that makes the most sense. So what we'll do for each scenario is to write out the likelihood function, the probability of observing our data with our proposed probability model, and then we're going to figure out, well, what value of the parameter is it so that that likelihood peaks? What value of that parameter gives us the best chance of producing the data set that we've collected? That's going to be known as the maximum likelihood estimate of our parameter, or just MLE for short. So you can imagine there's probably a lot of statisticians out there that probably named their baby girls Emily. That would be the best name, I think, for a baby for a statistician. Now, in general, when we go and try to maximize the likelihood function, we'll be using fitdist for the most part to do this numerically. But from a mathematical point of view, if we want to hand derive these expressions for the maximum likelihood estimate, very often it's actually easier to not maximize the likelihood directly, but to maximize the log of the likelihood instead. We'll see why in a little bit, why that equation is a little bit easier to maximize. But the nice thing is that we get the same answer both ways. If we maximize the original likelihood or maximize the logarithm of the likelihood itself. Since the log is a monotonic function, it turns out that the likelihood and the log likelihood both peak at the same values. So to pull off this maximum likelihood estimation procedure, step number one is to write out the probability of observing your data based on the probability model that you're using to fit. Now, normally this involves assuming that we're dealing with an IID sample, a random sample, so that each observation is coming from that same probability distribution and all of the values are independent of one another. So xi, twiddle IID f, each observation of x, x1 the first, x2 the second, x3 the third values we've collected, are all coming from the same PDF or PMFF. They're all independent of one another. And so that's the playground that we're going to assume that we're living in. And that assumption helps us to make the math a little bit easier so that when we try to write out the probability of that particular combination of values that we've collected, that just works out to be the product of the PMFs or the PDFs evaluated at each one of the individual data points that we've collected. So once we've written out the likelihood, the MLE procedure says, okay, pick the value of theta that provides the likelihood with a peak. Find the value of theta so that the probability model has the best chance of reproducing the data. Find the value that maximizes the likelihood. And that value of theta, put a little hat over it to denote that that's your best guess for that parameter of the probability distribution. So the one caveat that comes with trying to maximize the likelihood is that sometimes a mathematical procedure for finding where the likelihood peaks by taking a derivative and setting it equal to 0 to find where the slope of that tangent line is equal to 0, where the maximum usually is. Sometimes that procedure is going to fail you, and you're going to have to graphically look at what the likelihood function looks like in order to find the MLE estimate. And that is almost always going to be the case when it turns out that the range of possible values of x is actually tied in to the unknown parameter theta itself. So for instance, if we had a uniform distribution that ranges between 0 and theta, between 0 and some unknown upper bound, actually calculus is not going to help us out. Fitdist, Wolfram-Alpha, not going to be able to optimize that function normally because the peak of the likelihood function, as we'll see shortly, will through this example, occurs actually at a location where the slope is not equal to 0. So first step of the maximum likelihood estimation procedure is to write out the likelihood, the probability of observing your particular set of data values. So in other words, what is the probability that capital X1, our name for the random variable of the first value that we've collected, is equal to little x1, the value that ends up being observed. And the probability that x2 is equal to little x2. Big X3 is equal to little x3, so on and so forth. So in general, we know that the probability of some combination of events is a really tricky thing to calculate unless each of those events are independent of one another, in which case we can calculate the probability of that combination of events just by multiplying together the probabilities of the component events. So the upshot is, if I want to know what's the probability of observing that particular combination of data values that I've collected, if all of the data values are independent, I can just write that out as the probability of observing x1, my first data value, times the probability of observing x2, my second data value, times the probability of observing x3, my third data value, and so on and so forth. And so when I want to write down the likelihood function, if I have a PMF, all I need to do is write out the formula for the PMF n times to represent the n different data points that I have, and then just go back and replace the x's by x1, x2, x3 accordingly. If I have a continuous random variable so that I have a PDF, a formula for f of x, I'm going to do the same thing. I'm going to write out n copies of the equation for my PDF, and then I'm going to go back and replace the x's with x1, x2, x3, and that's going to mimic the process of just multiplying together the component probabilities of that combination of values that I've observed. So let's work through an example so we can see how this works. So let's imagine that we're dealing with a geometric distribution, and specifically xi, twiddle iid, geometric p. So each value I'm collecting, x1 the first, x2 the second, etc., are all coming from this geometric distribution. They're all independent from one another. And the parameter that I want to estimate from the data is p. So the formula for the PMF of a geometric distribution is just 1 minus p raised to the x power times p itself. You remember the geometric distribution is counting at the number of failures before that very first success. A success has probability p, a failure has probability 1 minus p. So for the probability of observing exactly little x failures, we need to have x failures all in a row, each with probability 1 minus p raised to the x, times that probability of success on that very last trial. So how do I get the likelihood of my random sample that I've collected, x1, x2, etc., based on my probability model? Well, what I'm going to do is I'm going to assume that it is an IID sample. It's a random sample. Everything is independent, so that the probability of observing my particular combination of data values just works out to be the product of observing each value by itself. So what I will do is I will write out the formula for the geometric PMF, multiply it by itself n times. So write out n different copies of that formula, multiplying it each one by itself. And then I'll just go back and replace the x's with an x1, an x2, an x3 to represent the different data values that I'll eventually collect in my random sample. And then I'm going to do some simplification. So to simplify that expression, what I'm going to do is I'm going to group similar terms. And this is where we need to remember how our laws of exponents work. So if I'm dealing with one big old product of a bunch of numbers, and each of the numbers have the same base, but potentially different exponents, the result is I get to take that common base and just raise it to the sum of all of the exponents of those terms in the product. So if I was multiplying together a squared times a to the fourth times a to the second times a to the third, common base of a, so the result would be a raised to some power. What's that power going to be? Well, I add up all of the exponents of the a's that I see in my product. So it works out to be a raised to the 11th power. Another key thing about exponents you want to keep in mind is that if you have a whole bunch of different numbers that are all raised to the same power, but potentially different bases, what you can do is you can group together all those bases in an expression, kind of wrap around parentheses around them, and then raise that expression to that common power. So a cubed times b cubed times a cubed again times c cubed could be written as a times b times a times c, all raised to the third power. And then finally, the last law of exponent that you really want to be familiar with, especially for likelihood estimation, is that if we have some number raised to a power, and that expression is raised to an additional power, those exponents multiply. So a cubed quantity squared would be a raised to the 6th power because that 2 and the 3 multiply together. All right, so let's group together terms in the likelihood for our geometric distribution. What we have is we have n copies of p that are being multiplied by itself. So that'll be p raised to the n power. Implicitly, the exponent of each of those p's is equal to 1. So common base of p, all the exponents add. There's n ones being summed together, so p raised to the n. And then what I see is that I have a common base of 1 minus p, all raised to different powers, all multiplied together. So the end result is going to be that common base raised to the sum of all of those powers. So I'm going to have a 1 minus p raised to the sum of xi, x1 plus x2 plus x3. Written in summation notation, that would be the sum from I equal to 1 to n of xi here. So after grouping the terms, I have a relatively simple expression for the likelihood of my data. Once I've collected x1, x2, x3, all the way up to xn, the probability of observing that particular sequence of values, that combination of values, is p raised to the n power, the number of data points I've collected, times 1 minus p raised to the sum of all of the data values that I've collected. The maximum likelihood procedure says, okay, well, let's choose a sensible value for p. Let's choose the value of p that maximizes the likelihood, so that the corresponding probability model, that corresponding geometric distribution, has the highest chance of reproducing the data that's collected. So where does that function reach a peak? Well, if I'm going to do this analytically, I want to find the place where that function, the slope of the tangent line of that function specifically, has a value of 0. When the slope of the tangent line is 0, that means I'm either at a maximum or a minimum. And so in this case, when the slope is equal to 0, I'll be having a maximum. I want to find out where that is. And so this is where the log trick generally helps out quite a lot. Because we know that the value of the MLE will be where the likelihood reaches a maximum, it's also where the log likelihood is going to be reaching a maximum. So I have a choice. I can either maximize the likelihood directly. Wolfram-Alpha can actually do this just fine. Back in the old days, though, before Wolfram-Alpha, it was very easy to instead consider the log of the likelihood instead and maximize that. So we need to review some tricks about logarithms. How do logarithms work? So key property of logarithms number one is that if I'm going to take the logarithm of the product of a bunch of different numbers, well, that turns out to be the sums of the logs of each of those individual components. So the log of a1 times a2 times a3, etc., is going to be the log of a1 plus the log of a2 plus the log of a3. So in product and summation notation, if I take the log of the product from I equal 1 to n of ai, that's going to be equal to the sum from I equal 1 to n of the log of ai. Very useful property of logs. The other useful property of logarithms that we want to be familiar with is when I take the logarithm of a number raised to a power. So the logarithm of a raised to the b power. Well, whenever you take the log of something raised to a power, that power gets to come out in front of the logarithm, leaving you with the log of whatever the base was. So the log of a raised to the b power is just b times the log of a. So it turns out that this is a very general trick, actually, that we can apply not only to this example, but just to likelihood estimation in general. That likelihood is going to be the product of the probabilities of observing x1 times the probability of observing x2, etc., etc. Using my tricks of logs, I can write out the log likelihood as just the sum of the logs of the formulas for the PMF or PDF evaluated at each of the x's. So the log likelihood would be the sum from I equal 1 to n of the log of the probability that x is equal to xi. Or if I had the PDF, the log of f of x evaluated at xi here. So back to our geometric example, we have that the likelihood is equal to p to the n times 1 minus p raised to the sum of all of the x's I will have collected. If I take the logarithm of that expression, well, the first thing that I note is that I'm taking the log of the product of two quantities, p to the n times 1 minus p raised to the sum of the x's. The log of a product is the sum of the logs. So I can reduce that just a little bit by saying, okay, that's the log of p raised to the n power plus the log of 1 minus p raised to the sum of the x's power. And then I can use my other rule of logs. What happens when I take the log of something raised to a power? That log of p raised to the n power becomes n times log of p, that n comes out in front of the log. And then the log of 1 minus p raised to the sum of the x power becomes the sum of the x's times the log of 1 minus p. Using that very general trick where just the log likelihood is the sum from I equal 1 to n of log of the formula of the probability that x is equal to xi. If I want to figure out, okay, well, what is the formula for the log of p of capital X equals to little x? My formula for the geometric, that works out to be log of p times, or plus x times log of 1 minus p. Just putting a summation notation right in front of that recovers the exact same value that I just derived. N copies of log p, so an n times log p, and I'm taking the sum over all of the x's of the expression x times log of 1 minus p. So log of 1 minus p times the sum of all the x's that I've collected. Same result, just a nice little shortcut that works out because of the math. But let's get into the meat of it. Let's figure out, okay, well, where does that likelihood function peak? What value of p should I take so that the resulting probability model has the highest chance of reproducing the data that I've collected? Well, unless you want to do the calculus by hand, here are some tricks on how to maximize this expression with Wolfram-Alpha. So obviously we can't write out the sum of I equal to 1 to n of xi in Wolfram-Alpha. So my trick is to just abbreviate that expression with a letter. And because we're taking the sum over all of the x's, I'm going to just abbreviate that with a capital S. And so I'll ask Wolfram-Alpha to maximize that expression just using capital S instead of that really awkward summation notation. And so in Wolfram-Alpha, here's how I can do it. I know that the function is going to reach a maximum where the derivative of that function is equal to 0, or the slope of that tangent line is equal to 0. So I can ask Wolfram-Alpha, okay, take the derivative of my expression, wrap that inside of parentheses, and ask it to solve for where the derivative is equal to 0 for p here. Now, notice when I take the derivative, I have that WRT, that with respect to, because there's a lot of different symbols in my expression. I have a P, I have an N, I have an S. I need to tell it, okay, well, what am I actually taking the derivative with respect to? What am I really hunting for? I'm hunting for a value of P. And Wolfram-Alpha will come back and it says, okay, well, P in this case is equal to N over N plus S. That's the value of P where that likelihood is going to reach a maximum value. So I'm going to put a little hat over P once again to represent that it's an estimate of what that parameter is, and it's going to be N over N plus the sum over all of the x's. And if I want to be really clever, I can multiply the equation by 1, just writing 1 as 1 over n divided by 1 over n, kind of go through that math, and what I would find that P hat would be equal to is just 1 over 1 plus the sum over all of the x's over n, but the sum of all the x's over n is just x bar. And so I can come up with a pretty simple rule for what the MLE estimate of P for a geometric distribution is going to be. P hat is just 1 over 1 plus the sample average. And that's the great thing about doing maximum likelihood estimation by hand, kind of figuring out just in terms of the general expressions for the PDF or PMF that I'm working with. I have a nice, really simple rule that tells me what I need to do with the data values that I've collected in order to come up with a great guess for what that unknown parameter is. My simple rule in this case is to measure the sample average, take 1 plus the sample average, reciprocal it, and that's going to be my value for P hat. Another example, let's try to figure out the MLE for the lambda parameter of a Poisson distribution. So I'm going to assume that I have a random sample from a Poisson PMF, so xi, twiddle iid, Poisson with parameter lambda. The first value I collect x1 is independent from the second value I collect x2, etc. They're all coming from this common Poisson distribution lambda. I want to figure out what do I need to do with the data to come up with a really good guess of what lambda might be. So if I use the maximum likelihood estimation method, what I need to do is to come up with an expression for the likelihood, basically the probability of observing the particular combination of values that I've collected in my data, a particular combination of little x1, little x2, little x3, etc. And so, with this independence assumption, the probability of observing that particular combination of x's just works out to be the product of the probabilities of observing each individual x by itself. And so, I'll do the same procedure as what I did for the geometric. I'm going to take my formula for the PMF of a Poisson distribution, and I'm going to create n copies of itself. I'm going to multiply each of those copies together. And then I'm going to go back and just replace the x's with the x1, the x2, x3, etc. to represent the different sample values that I've collected. So that'll give me an expression for the likelihood, and then I'm going to try to combine terms to an extent where the equation looks a little bit simpler. So I look at it, and what I see is I have an e raised to the minus lambda power multiplied by itself n different times. So whenever I have a common base multiplied by itself a bunch of times, potentially raised to different exponents, the result is that common base raised to the sum of all the exponents. So I have n copies of a minus lambda. The sum over all those exponents would be minus n times lambda. I see that I have a lambda raised to the x1, a lambda raised to the x2, same sort of situation, a common base of lambda raised to a bunch of different exponents. The result of taking that product is going to be that common base lambda raised to the sum of all the exponents, x1 plus x2 plus x3. I'll write that in summation notation, the sum from I equal to 1 to n of xi. And then I see I have an x1 factorial times x2 factorial times x3 factorial. I can write that in product notation as the product from I equal to 1 to n of xi factorial. All right, so in this case, what I'm going to try to do is to maximize the log likelihood, a little bit easier to approach mathematically. So if I write out my equation for the log of the likelihood, I have a log of e to the minus n lambda times lambda to the sum of the x's divided by the product of the xi factorials. Well, that's the log of two things multiplied by each other and divided by the third. And my rule of logarithm says that the log of a times b is the log of a plus the log of b. The log of a divided by b is like the log of a times b raised to the minus 1 power, works out to be the log of a minus the log of b. So I can rewrite that expression as the log of e to the minus n lambda plus the log of lambda raised to the sum of the x's minus the log of the product of those factorials. And I'll use my rule of logs to rewrite the log of e to the minus n lambda, taking the power of e out in front. So minus n lambda times the log of e plus the sum of the x's times the log of lambda, taking that exponent out in front. I'm not going to really simplify the log of the factorials. I could if I really wanted to, but in this case, the derivative doesn't really depend on that component. And so what I have left is an expression for the log likelihood that is fairly easy to differentiate with respect to lambda. I want to differentiate it. I want to take the derivative because I want to figure out where that derivative is equal to 0. That derivative tells me the slope of that tangent line, and I want to know where that slope is equal to 0. That's going to be where this likelihood function reaches a peak. So taking that derivative of the log likelihood with respect to lambda in this case gives me an expression. I'm going to set that equal to 0, and I find that the solution to that equation, the value of lambda that makes the slope of the tangent line equal to 0, the value of lambda that gives my log likelihood a peak, is where lambda is equal to the sum of all of the x's divided by n. So I'll put a little hat over it to represent that's going to be my best guess for what lambda is. And since the sum of the x's over n, however many there are, is what the sample average is, I come up with the very simple rule that if I want to come up with a great guess for the lambda parameter of Poisson, all I got to do is take the sample average. Lambda hat, the MLE, in this case, is just x bar. All right, if I didn't want to do that by hand, if I wanted to rely on Wolfram-Alpha, really not so bad either. What I can do actually is I can really even just forego writing out that formula for the log likelihood if I want, and literally just throw in the formula for the likelihood after I've combined all those powers until Wolfram-Alpha to figure out where the slope of the tangent line is equal to 0. So I'll abbreviate lambda just with a capital L. I'll abbreviate the sum over all of the x's as just capital S again. And I'll replace the product of all the factorials of the x's just with a capital F. And I'll ask Wolfram-Alpha to take the derivative of that expression with respect to lambda, with respect to L in this case, and then solve where that equation is equal to 0 for lambda. Figure out where that slope of the tangent line is equal to 0. Wolfram-Alpha lets us know that there are 3 solutions. I'm going to have to go and hunt for the one that's appropriate. One solution is that lambda is equal to 0. Now, that doesn't make any sense. I'm trying to solve for lambda in terms of the data that I've collected. The other second solution doesn't really make much sense to me. We could ignore that one. The bottom one looks like we're in business. So L is equal to capital S over N. So I just need to replace my abbreviations to what they were representing. L was lambda, S was the sum of all the x's, so I find that my lambda hat is just the sum of all the x's over n, my expression for x bar. All right, another example. Let's imagine that we have collected an IID sample from the following PDF. So 2 over theta times x over theta quantity squared times e to the minus quantity x over theta raised to the 3rd power. So if all of the data values that I've collected, x1, x2, x3, etc., are independent from each other, and they're all coming from this common distribution, what do I need to do with the data in order to come up with a great guess for what theta might be? What is the MLE, the maximum likelihood estimator, for theta in this case? So I'm going to go through that same process. What I'm going to do is really rely on the fact that I'm assuming that this is going to be a random sample, and so that the probability of the particular combination of values that I've observed is just the PDF evaluated at each one of those different x's, x1, x2, etc., multiplied by each other. So I'll start out by taking my expression for the PDF, multiplying it by itself n different times, and then going back and replacing the x's with the x1, the x2, the x3, etc. I can combine similar terms and I can get a value out for the likelihood. Now, in this case, I actually want to illustrate working with the log likelihood directly because why not? Kind of good to know the entire bag of tricks that's available to you. So let's actually write out the formula for the log likelihood by taking the sum of our expressions for the log of the PDF itself. So in this case, the log of the PDF would be the log of 2 over theta times the quantity x over theta squared times e to the quantity minus x over theta raised to the third power. So using my rule of logs, well, I see I'm taking the log of the product of three things, a times b times c. And so the log of a product is the sum of the logs. So the log of the PDF works out to be the log of 2 over theta plus the log of x over theta quantity squared plus the log of e raised to the minus x over theta cubed. And I can just use some more properties of logs. The log of 2 over theta, well, the log of the quotient of two numbers is the log of the numerator minus the log of the denominator, so log 2 minus log theta. The log of x over theta quantity squared, well, the exponent gets to come out in front of the log, and so I'd have the log of x over theta once again, the log of x minus the log of theta. 2 gets multiplied by each of those. And then finally, the log of e raised to the minus x over theta raised to the third power. Take that exponent out in front. So I'll take out that minus x over theta raised to the third power, then multiply that by the log of the base, the log of e. But the log of e is just equal to 1. And so I get an expression for the log of my PDF. And the log likelihood is just one step away. I just slap a summation symbol out in front, taking the sum from I equal to 1 to n. And so I have n copies of log 2 in that sum. So the log likelihood would be n times log 2. If I take the sum of 2 times log of x, well, I'd have 2 times the sum of the log of the x's from I equal to 1 to n. I have n copies of minus 3 times log of theta in my sum, so that would work out to be minus 3n log theta. And then I have x over theta raised to the cube third power, summed from x equal to, or I equal to 1, 2, 3, all the way up to n. So I have my formula for the log likelihood. The MLE estimate is going to be where the slope of the tangent line of that function is equal to 0. I can find that by taking the derivative and figuring out, well, where does that derivative equal to 0? That derivative is telling me the slope of that tangent line. And so after a little bit of math, what I can find is that I have a relatively simple expression for my MLE. So I put a little hat over it to denote that that's my good guess for what theta might be. That's my MLE in this case. And once again, it provides me with a really nice, insightful rule as to what I need to do with this data in order to come up with that great guess of theta. So it definitely wouldn't be something that I could have anticipated beforehand. It turns out what I want to do is take my collected data values, cube all of them, take the sum of all the cubes, then take the cube root of that result, and then divide by the cube root of the sample size, the number of values I've collected. Who knew? But by going through the maximum likelihood procedure, we have this really nice simple rule of what we need to do with the data to come up with that MLE estimate. Now, if you didn't want to do all that by hand, and I don't blame you, we can do that in Wolfram-Alpha with not too much effort. We'll start out with our formula for what the log likelihood is after grouping together all of those relevant terms. We'll ask Wolfram-Alpha, all right, take the derivative of that expression with respect to theta in this case, and then solve that equation where that's equal to 0 for theta here. And then we have to hunt through the different solutions and figure out which one makes the most sense. And in this case, that second one is the one I'm going to hone in on. The other ones are just actually other ways of writing out that same value. And so all I have to do is to replace the abbreviations that I use to represent some of those quantities in Wolfram-Alpha, like capital S being the sum of xi cubed, z being the sum of the logs of the x's. And so I'd find that I've recovered the same MLE estimate. Basically take the sum of the cubes of all your data values, take the cube root of that, and then divide by the cube root of the sample size. So back when we were discussing the maximum likelihood procedure, we talked about step 1 is to write out the probability of observing your data with that probability model, write out the likelihood. Step 2 was to figure out where that likelihood peaks. And normally that involves just figuring out, well, where's the slope of the tangent line equal to 0? So take the derivative, set it equal to 0, solve that equation, and then you're done. But that doesn't work every time. And the instances where that doesn't work is where the likelihood actually reaches a peak where the slope of the tangent line is not equal to 0. And normally this occurs whenever theta is actually tied into the possible values that x can achieve. So here's an example of this, and keep this in mind. Whenever you see that the possible values of x actually depends on theta itself, most of the time, calculus, Wolfram-Alpha is going to fail you because the peak of the likelihood is not going to occur where the slope of the tangent line is equal to 0. So let's see how that happens with the following example. So let's imagine that the PDF that's generating my data is a uniform distribution. 0 is the lower bound, and 2 times theta is the upper bound. 2 theta so that the average value is just equal to theta itself. And so the formula for the PDF of my random variable x is just 1 over the upper limit minus lower limit, 1 over 2 theta. The possible values of x could be anywhere between 0 and 2 theta. So we see theta being tied in to the values of x that can potentially be observed. So let's try to estimate the MLE. What we'll do is we'll write out the probability of observing our random sample. We're going to assume we have a random sample, each x that we've collected, x1, x2, etc., coming from the same distribution. They're all independent of one another, so that the probability of observing our data, that likelihood function, is just our formula for the PDF multiplied by itself n different times, then going back and replacing the x's with x1, x2, x3, etc. In this case, x doesn't actually appear in my equation for the PDF, so it's particularly simple. I just have n copies of 1 over 2 times theta multiplied by each other. The result's going to be 1 over 2 theta raised to the quantity of n. So taking the log of that expression, maybe we'll figure out where the log of the likelihood peaks. The log of the likelihood, well, we'll take that exponent out in front and take the log of the base. So n times the log of 1 over 2 theta. Well, 1 over 2 theta is really 2 theta raised to the minus 1 power, so we'll take out that minus 1 as well. So minus n times log 2 minus n times log of theta. All right, so far so good. If I were to use calculus to try to figure out, well, where does this likelihood function peak, I would take the derivative with respect to theta, and I would figure out, okay, well, where does that derivative equal to 0? Well, in this case, the derivative of the log likelihood is just minus n over theta. So if I try to figure out, well, what beta value of theta results in that equation equaling to 0, I don't really find the solution here. So minus n over theta gets closer and closer to 0 as theta gets bigger and bigger and bigger and bigger. But there is no value of theta for which that derivative is exactly equal to 0. So there is no place on this likelihood function where the slope of the tangent line is equal to 0. So what's my solution? What value of theta maximizes the likelihood? So let's approach this problem graphically so we can see where the maximum likelihood estimate ends up being. So if I go back and look at my formula for the likelihood of the data, it's 1 over 2 theta, that quantity raised to the n power. If I make a plot of that function versus theta, what I find is actually the likelihood gets larger and larger and larger for smaller and smaller values of theta. So based on the graph, it looks like in order to maximize the likelihood, I need to take theta as small as I possibly can. So I'd like to get it as close to 0 as possible. And now here's where a little bit of logic has to come into play. So I want theta to be as small as possible, but remember the definition of our PDF. All of the x's that I'm collecting have to be between 0 and 2 theta, so I can't actually take theta to be arbitrarily small. If I go and look at the largest value of x in my random sample, well, I know that theta has to be larger than that maximum value over 2. That maximum value has to be less than 2 times theta, so theta has to be greater than the maximum value of x over 2. So while I want theta to be as small as possible, I have to make sure that theta is larger than the maximum value of x over 2. Otherwise, it would have been impossible to observe that data. Let's imagine I observed a value of x of 9.8. Well, I couldn't take a value of theta of equal to 1, because in that case, the probability model would have said that my x's would have ranged between 0 and 2. A value of 9.8 would have been impossible to observe, so technically the likelihood if theta was equal to 1 would be equal to 0, because there's no way I could have observed a value of 9.8. So in this case, I had to solve for the maximum likelihood estimate both graphically and with a little bit of logic. I realized that the likelihood was getting larger and larger and larger as the value of theta was smaller and smaller, but there was a limit to how small I could take theta to be. Based on the definition of the PDF itself, I couldn't take theta to be any smaller than the maximum value of x over 2. So in this case, my MLE, my theta hat, my good guess of what theta is to look at the largest value I've collected in my sample and just divide that by 2.